Okay, great. So good morning and happy, what's today? Thursday? Yeah, Thursday. Happy Thursday. All right. So where we last left off, the administrative bits before we begin. Um, Project number two, I stretched the deadline 2 more days later, so it's a week from today at 11:59. I have to recalc some stuff on the schedule because there's a homework one that's going to be coming out. The purpose of the homeworks is to reinforce more of the theoretical material. AutoGrader, there were a bunch of fixes, some bugs in how AutoGrader works, some things that didn't work the way that they are supposed to work. I posted that on Slack. I won't relitigate them here, but I'll also show you some Gradescope AutoGrader isms, but the back end has been updated as of last night. If you are curious, it's a cloud-based environment. You have to stage a container with a Linux image, and then you automate some, you write some automation that stages stuff based on the assignment, and then it generates output, consumes that JSON file, and then displays what you see when you submit on Gradescope. So there's a bunch of stuff that you don't see certainly affects you, and those bugs certainly weren't helpful for things that didn't work the way they're supposed to. Nonetheless, it's fixed now. How's everybody doing on project two? People have started already discussing implementations. Okay. And so one of the things I'm going to strongly recommend is if you are in an IDE type environment, it's really helpful to write your code so that you can view and inspect things to help you understand how the environment works. I'm a strong proponent of you doing debugger walkthroughs, right? It's really important. It helps you to understand how parts of the code interact with one another in a much better way than if you were just to look at Python files, right? Let the debugger and the tools help you, whether you're using Visual Studio, JetBrains, or what have you. It doesn't matter. They're all doing roughly the same things these days. Okay? All right. Any questions? No? Let me make sure this is on. All right. So where we last left off, we talked about properties of heuristics and their optimality. And we said that there's this thing called admissibility. And admissible heuristics afford you A-star search with these evaluative measures that consist of two components that we call G of n and H of n, where G of n is the path cost and H of n is the heuristic or estimate of the path from a particular node n to the goal. And so we put these two things together, and our consideration where we left off was on properties of the heuristic and its ability to find optimal solutions to the search problem. And so we talked about two properties. One was admissibility, and then we talked about a stronger property, consistency, namely satisfying the triangle inequality. And so consistent heuristics are admissible, but admissible heuristics are not necessarily consistent. So the space of admissible heuristics contains the space of consistent heuristics. Any questions about this? No questions? No? All right. And so then how you craft your heuristic, you have to ensure in some fashion that this heuristic is an underestimate of the path cost to the goal from a particular node with which you instantiate it. And so the heuristic, we said, where we left off, can afford you savings on those parts of the state space the state space that you explore. And so here we have a notional expansion of the Romania road trip problem. And we're given for that a map and each node corresponding to a city. And each action corresponds to taking a roadway or traversing a length of road. And each one of those roads or actions is decorated in the graph with the mileage. And so the goal then with our A-star search in this problem is to find a solution path, i.e., that route, as it were, to Bucharest, which is our goal, that has the minimum cost. And so in that case, our example, and that motivating example, was an admissible heuristic, which is a straight line distance. And as we motivated with this idea of a Route 20 road trip, the straight line distance does not take into account the exact geometry of the roadway system. And so in the worst case, this heuristic is going to be precisely the same length as a segment of roadway. But in most usual cases, the roadway is going to turn and twist and bend in ways that the heuristic does not straight line. So the heuristic is always going to be an underestimate, i.e. it's going to give you a shorter distance than the actual path cost of the roadway. Okay. And so with this, you're exploring, because when you use this evaluative measure, which is this composition, G of n plus H of n, you're exploring using a priority queue those nodes on the frontier that have the smallest value, right? So it's a best first search, bless you, using this G of n plus H of n. And so as such, you're going to consider nodes on the frontier that have smaller values. And where we left off, we gave this sort of visualization. And in this, when you expand a rod, you're going to then, on your next try, you're going to expand Sibiu. Now, in expanding Sibiu, you ignore the subtree in this graph rooted in Timisoara and in Zerent. And as such, unlike breadth first search, you're not going to explore those subtrees. You're going to focus in on Sibiu, driving down, effectively saving yourself the time complexity in exploring parts of the tree that might not appear fruitful for where a goal might be located. Does that make sense? Okay, so this idea of effectively eliminating from consideration. And it's not really eliminating from consideration, it's preferring one alternative. And in doing so, you're not going to suffer the consequence of exploring those things that are rooted in Timisoara and in Zerent. So effectively, you're saving time by so-called pruning, right? And this means that as you tinker with the heuristic, you're changing this f of n, this evaluative measure. And depending on the characteristics of your heuristic, you can direct the frontier in ways that effectively afford you a savings, both in time, the number of nodes you evaluate, as well as in space, the number of nodes you have to remember as you're encountering more nodes as you expand frontiers. Does that make sense? Any questions? No? Okay. And again, excuse my voice. It's cold and flu season. I have all my vaccines and all that stuff. But anyways, so you can take advantage of an inadmissible heuristic. For every rule and every concept, there's a counterexample with all sorts of properties that people have studied over the decades. And so, yes, you absolutely would like an admissible heuristic, and in the best case, a consistent heuristic, because those have nice desirable properties. But if you relax this assumption, you can still exploit various properties depending on that relaxation on your heuristic when you compose this evaluative measure, your f of n equals g of n plus h of n. And so it's important to prune, and you can get memory and time savings and by allowing inadmissible heuristics in an A-star search. Okay. And so there's one such approach, the so-called weighted A-star search. And what this weighted A-star search does, it says, I'm going to count my heuristic contribution to my evaluative measure based on some weight for a weight that's greater than one. Okay. And so with this, and this illustration is in the book, on the right-hand side, and this is a graph-based search problem, we talked about this idea, oh, I don't have my pen, of contours. And these contours correspond to regions of your state space for which this evaluative measure is less than equal to a particular value. And so you imagine then if our initial contour, and I'll just sort of illustrate with my mouse here, was here. Once you have a particular evaluative measure, you're going to be searching all of the nodes within that bound of that contour line. And then once you exhaust all those nodes within that value of the evaluative measure, you're going to increase that contour by considering an evaluative measure that's a larger value. So what's going to happen now is you're going to start searching nodes that are inside this new value of the contour. And so in effect, looking at the progression, if it's monotonically increasing this contour, looking at the progressions of contours, if you can change this f of n in some way, and a weight can do that, a weight on the heuristic, you can change the shape of this contour to proceed in certain types of steps. And when you increase this weight or set this weight enough, you can force this contour to jump forward, almost looking like a depth-first search rather than spreading outward, which looks more like a uniform cost search or a breadth-first search. Does that make sense? Any questions? Yeah. And like past the second row, you're blurry. So just it's easier to read a screen with my glasses off. All right. And so with this contour on the right-hand side, you can see that this contour looks like it's kind of jumping forward, right? Instead of spreading outwards. And in doing so, you're effectively telling your search algorithm, don't look left and look right, so to speak. I want you to go forward faster and further, in effect, pruning. Let me try a different color, see if I can come up with a good visualization. It's doing this. In effect, pruning away from consideration those nodes which would tend to be out towards the sides in this visualization. Does that make sense? Any questions? No? Okay. And so if your optimal path is outside of the contour, as you're tinkering with your evaluative measure by weighting the contribution of your heuristic, yeah, you're going to have a solution that fails. Because in the case on the left-hand side, because it goes wide within these boundaries, exhausting all the nodes within the contour, if it exists within the contour, it's going to find it, and then you increase the contour. But when you focus it going forward by weighting this heuristic, there's a chance that your solution might be out here on the sides and not in that region where the contour is projecting forward, okay? But if there's an optimal solution within the contour, your cost with this weighted solution is going to be in the interval between C star, the optimal cost, and WC star, a factor of this weight that you have, okay? And so you can, by taking this weight, effectively prune away large parts of your state space by not considering them for when you explore the frontier. But that there's a consequence of that, and that consequence is on the path cost, the optimal cost, okay? And so effectively what you're doing is you're affording a band of costs. You're trading off optimality away from C star against efficiency, projecting forward in the state space faster to try to have memory savings or time savings. And that's really the trade-off. You either are very efficient or you are optimal. And like any practical problem, there are sort of these competing forces that you have to trade off on. And it really depends on what you're after for the application you have in place. Okay. Any questions? No, no questions. Well, quiet. All right. And so heuristic search in general, in the framework of weighted search, you can think of all the different types of searches that we've touched upon thus far as special cases of weighted search. Of course, our A-star search, our weight will be 1. You have an equal weight contribution, so to speak, of your path cost G of n and your estimate to the goal H of n, our heuristic. In the case of uniform cost search, you're using just the path cost, and each one of those actions have a step cost of 1. And so you can think of this as the weighted version of the heuristic search or A-star search with the weight equal to 0. In the case of greedy best first search, well, you can think of it as not considering the path cost whatsoever. You're just using the heuristic value, this evaluative estimate of the cost to the goal. And you can think of that as just only considering that contribution for the heuristic, or the weight is equal to infinity. And then lastly, weighted A-star search, our weight is greater than 1, not infinity. I always love notation like that, less than infinity, okay? Is that a trillion? Is that a million? Or what have you? But nonetheless, we have our weighted version of A-star search, okay? All right. Any questions? Yeah. And so there are considerations for bounds on storage, right? Because, of course, computing storage is finite, and you have to manage that in many cases, especially for large, complex state spaces. And the storage effectively arises due to 2 data structures. One is the frontier. That's unavoidable, right? You need the frontier because that's how you push forward in exploration of these states, or if it's a tree structured search as well. And the other is the reach data structure. Now, this reach data structure, we will see when we get to the code, can be of 2 sorts. One is to control the revisiting of states in the environment as you explore the frontier or expand the frontier. And the other is as a kind of caching mechanism. You're storing nodes, and these nodes could also be associated with a notion of best cost. And so if you have 2 solution paths, and these 2 solution paths both go through the same node, the second time you encounter that node, if the path is an improved cost, then rather than just using the reached data structure as the criteria for whether or not you can explore, you can update your concept of what the best path is. So it's almost like a caching mechanism where you say, okay, for this node, what is the prevailing best cost that I've encountered on the many or potentially many solution paths that might pass through it? Okay, all right. Any questions? No? I can feel my left eye twitching. That's weird. So I'm not looking at it, just eyes twitching. Happens sometimes. All right. And so typically, the frontier data structure is going to be small and reached, especially for something where you have a high complexity like breadth first search. You're going to be populating a lot of nodes on this reached data structure. You might say, okay, well, in my implementation, I'm going to just keep my nodes in only one place. Yeah, you could try to do that, and that's certainly a reasonable consideration. If you're only using one data structure, then you don't have to keep things around multiple times, okay? But then this is going to complicate your algorithm, right? Because typically with the frontier, thus far, we've seen that we pop things from the frontier, right? Once we evaluate them, once we expand them, they're removed. So the frontier is going to have nodes placed on it, conceivably the successors of a node we expand. But then in kind, it's going to grow smaller on each turn every time we try to do our analysis. So one of the other approaches that people have tried for trying to limit our storage is a so-called beam search. And what a beam search does, it says, okay, well, rather than placing any node that I encounter on the frontier, making it a candidate for expansion, I'm only going to limit k many nodes that satisfy some criteria to be on the frontier, right? So this idea of the k best evaluative performance, evaluative measures are going to be represented on the frontier. Now, of course, when you think about that, you're saying, I just want to maintain this idea of the best places in my state space to expand, to explore. And that might seem reasonable because if you're going to be taking the node with the best evaluative measure off the frontier anyways, you're effectively pruning those nodes which have really bad evaluative measures that might be towards the end of our priority queue, right? So in that case, yeah, that could work, but it can be suboptimal because sometimes you find that nodes that might seem like they're bad could lead to some other solution path that ends up ultimately being better. So this can help you with your memory savings, but it's incomplete if only a single solution path, optimal solution path exists. It might not always find it, and it's suboptimal. It can return a solution path, but it might not be the best solution path available. Any questions? No questions? No? And then there's IDA star, iterative deepening A star. And it's like iterative deepening, and recall iterative deepening, we set a depth limit and we explored at depth 0, 1, 2, 3, and we incremented this depth limit up to some point. And so this kind of gave you the benefits of depth-first search using something that looked like breadth-first search, which is kind of nice. With IDA star, it's an A star search. So you have this evaluative measure, F of n equals G of n plus H of n. But in this case, you have a cutoff F score, right? Similar to how you had a cutoff depth. In this case, your cutoff is based on the evaluative measure. So in essence, what you're doing is you're saying, and I'll just kind of draw a caricature up top, you're saying, I want to try a contour to explore my frontier. And then I'm going to increment that contour relative to the next value of my performance measure F that exceeds the current contour. So you're in essence saying, I expanded the frontier and I encountered a node that's outside of that contour in its F value. So then you increment it and you try that on the next round, the search at the next version of the contour. So just like iterative deepening search, IDA star does this monotonic exploration, but it's based on increments of the contour value. Does that make sense? Any questions? No? All right. All right. So, all right, there we go. So in this version, remind myself. Yes. Okay. In this version, so-called recursive best first search, of course, it pursues the best evaluative measure F in terms of nodes it's going to prefer to explore for the frontier. But in this case, it identifies also the second best. And what it does is takes this second best F value and it kind of saves it. It propagates it back as this idea of this is my alternative where I'm going to explore the frontier should what I understand to be the best evaluative measure doesn't work out well, right? If it's not the best, maybe second best might lead to an improvement. So we start out and it's recursive. We initialize our problem. And then we check as usual for the goal state. We get our successors. We want to see if we've exhausted our successors. We back up, unwind that recursion, and then call. If we do have successors, we take each of those nodes that are successors and we find the one with the max value for this path cost. Max meaning quote unquote the best. Okay. And then we iterate in our loop here and we look at the one with the lowest value. And if our notion of best is greater than this limit, we back up and then we search the alternative. Okay. Any questions? No. So let's have a visualization. And this is using the Romania search problem. We start out in Arad. And if we expand Arad, we have three values. We have rather three successors, Sibiu, Timisoara, and Zarent. And Sibiu has the lowest evaluative measure, 393. So we're absolutely going to pursue that because it's placed on the priority queue, and that's what gets explored first. But you'll notice here, CBU is decorated with the value of the second best alternative, and that second best alternative is Timisoara, right? So at each node, you have not only its evaluative measure, but you have the second best one as this backup should what you're doing, the primary, not work out well. Okay. So then we expand CBU, and when we expand CBU, we have Arad, Fagaras, Oradea, and Rimniku Valeka. And Rimniku Valeka has an evaluative performance measure, cost, F of N, of 413. So it's the smallest. But the second best is Fagaras at 415. So we're going to now expand the frontier from Rimniku Valeka, but we also keep in mind this 415. Okay. So now from Rimniku Valeka, we expand the frontier. We have three successors, Craiova, Patesi, and Sibiu. And notice Sibiu appears again, right? We've encountered it again. It's a graph-based search in this case. So here we see that the best evaluative measure is Patesi. It's 417. But 417, yeah, it's greater than 413, but it's also greater than this second alternative. And so in that case, it might not be fruitful to explore further Patesi because I already have in my pocket this knowledge of something that is a better alt. Does that make sense? So now I back up and I go to Fagaras and I expand Fagaras. When I expand Fagaras, I get two children, Sibiu, and you notice Sibiu appears again, right? And I have Bucharest. Fagaras, okay, it was the smallest as 415 because of that backup at Rimniku Valeka. And the second best is Rimniku Valeka at 417. Okay. Well, you might ask, well, didn't I explore that before? Yeah, I did. But if I'm expanding Fagaras, the second best was still Rimniku Valeka. Does that make sense? So now at Fagaras, and this is where that memory of the second best alternative is of value, I go to expand the frontier at Fagaras, and I get two children, Sibiu and Bucharest, at evaluative measures of 591 and 450, respectively. And Fagaras says, well, I could go and add these to the frontier, but I have something in my pocket, this knowledge of Rimniku Valeka, which was 417. So maybe it's not fruitful to go further with my children. Let's back up and go back to Rimniku Valeka. Okay. So we go to Rimniku Valeka and we expand the frontier. It has three children, Craiova, Patesi, and Sibiu. And the smallest cost is Patesi, again, which was 417. And the second best is, where was that? 27. 417. 526, 417, 553. Where did the four? Yeah. Okay. That's weird. Yeah, that might be an error. Okay. So I explore the frontier from Niku Valeka, and the cheapest child or best measure for the child is Patesi, which has an evaluative measure of 417 in this. Yeah, 417. Okay. So the second best, it should not be 447. It propagated it from the parent. I see. I see. Yeah, it's yeah. All right. So nonetheless, we expand Patesi, and Patesi has three children. One is Bucharest, Craiova, and Nicu Valeka. We see that Bucharest is 418, and 418 is worthwhile to pursue because certainly it's more than Patesi, but it's less than either of the alternatives alongside Patesi. Okay. Does that make sense? All right. And so with this idea of the second best alternative, you're going to back up if you don't feel that it's a fruitful endeavor to further pursue the successors that you encounter as you expand the frontier. Okay. Any questions? No, that makes sense. All right, so that's all I had for the rest of the material. And in terms of the material, we're actually a little bit ahead of schedule. So what I'd like to do with the balance of today, we have about half an hour, is to walk through considerations for the code. So I'm going to exit the slideshow and bring up my debugger. And I have my solutions here, and we'll just take a look at various aspects of the code. All right. So why don't questions? All right. So let me go back to Zoom, and I'm just going to share this desktop. That's a lot easier to switch back and forth between windows. All right. So I have my solutions here, and let's go ahead and let's run the auto grader. The auto grader can accept a command line option -Q, and you give it the question number, like question 1. And I run it, and it'll score it, but it also gives you a little bit of information about the test case that it's running against the question. And so each question has a bunch of test cases, and each test case has a points value, and those points valued add up to a maximum number of points. There are two different types of tests. One are pass-fail tests, and the other are partial credit tests. These partial credit tests typically have performance criteria associated with them. And based on different thresholds of that performance criteria, you're awarded increments of percentages of the maximum points. Now, certainly with this partial credit test, how the autograder is implemented is that it's considered a failure in terms of the test reporting if you don't satisfy the best of the thresholds, but it still awards you that requisite amount of points. And so in the case of one of the questions, I think it was question 8 or 7, I can't remember, there was an extra credit threshold where you got 125% of the points associated with that test case. If you got 100%, it would still return failure. But if you look at what it assigned you, it still assigned you the points. That's just an idiosyncrasy of the autograder environment. Okay. All right. So here, this is question 1, and you can have autograder pull out individual questions. Let me clear the screen. And let me run question 2. Question 2 has a different set of test cases. One of the things you can ask autograder, go back to Q1, is to give you the verbose output with a -P. So I'll do -P here. And one of the things it does is it gives you both, if it's a maze, it gives you the maze layout, and it gives you what the solution is, what your answer was, so that you can have some information that helps you arrive upon what went wrong. Okay. And so this is the verbose version of the test of the test. And so if we go up here for question 1, it shows you a diagram of the graph, and then it shows you what the transitions should be and your solution. Okay. All right. And this is why you should be using, or you have to use, the data structures that are from util.py, because there's instrumentation in those that the autograder uses. And so if you're using stack, use the one from util. If you're using Q, use the one from util, please. Okay. Any questions? No? And then if you run autograder without any parameters, it's going to cycle through all of the questions and all of the test cases for each question. And so here, the reporting is for all of those questions, all 8 of them. And so one of the things you'll see that it's 105 and not 100, and that has to do with question number 7. All right. Question number 7 has 2 components. It has 17 test cases, and then an 18th test case is a so-called partial credit question. And that partial I can't say that. Partial credit question, say that fast. The partial credit question is associated with 4 points, and you're awarded based on performance thresholds, 25% increments, 0%, 25, 50, 75, and 100. But that last increment is extra credit, 125%. And so if you get the 100%, wonderful. It'll still say I failed, but award you the 100% for that part of the question. And so because of that, 17 plus 4 is 21, right? So I had to change the scoring criteria because AutoGrader was breaking in ways that it should not have. Okay. All right. Any questions? No? All right. So let's bring up PyCharm. And in PyCharm, I've already set up a code environment. Wow, this is small. When you get older, your eyes, you need to have big fonts, right? Let's go to search.py and let's consider question number 1, which is depth first search. Okay. And so for question 1, depth first search, you're literally implementing the algorithm that's in the book. Yes, the algorithm gives you breadth first search, and depth first search is just the same type of search. The only difference is the data structure. In depth first search, you're using a stack. In breadth first search, you're using a queue, right? So if you can implement depth first search, it's a one-line change, 2-line. There's a 2-line change, well, really one-line change to implement breadth first search. Okay. All right. So here, let's start out. I'm going to stop the debugger and I'm going to restart the debugger. And I have a breakpoint inside of the clean code provided for depth first search. One of the things that's immensely helpful, so let me start the debugger. Okay, so run games, let's continue. Game run, let's continue. Step in. And it's just really helpful to step your way through the code to get an understanding of what these things do. So I'm going to step into this. It does a deep copy of the game state. Question? No? All right. And let me go into agent register. And for these search problems, depth first search, breadth first search, uniform cost search, when it calls into your agent, you're going to return back the entire path, the solution path, right? It's different from other types of search. So I'm going to step in here, and on search function, that's where it calls into your code. And so here I'm in the depth first search entry point, which is where your implementation goes. And one of the things that I like to do is use variables a lot when I set things. Yeah, you could use Lambda functions, you could implicitly populate arrays, but I like to assign things to variables because it makes it easier to debug, right? So in this case, we're going to call get start state, and it's useful to take a look at what these representations are. So I'm going to call these first 3 things. So in the debugger, I see that my start state is a 2-tuple, and that 2-tuple represents the position in the grid world where PacMan begins. And so if you're going to represent state, that state, as far as the PacMan graph is, in this example, is going to be the location, all right? And then likewise, successors. So let's take a look at successors. It's a list of 3 tuples. So let's expand that. The first position of this 3-tuple is the location in the grid world, right? In the maze world, 5, 4 in this case. The second position is the action, go south. And then the third position is the step cost, right? And so I highly recommend you tinker with some of the data structures, set some variables, walk through the debugger to help you understand what these pieces of information mean. Now, absolutely, you could go into game state object and go into game state data and then go through the code. It's a lot easier to let the debugger tell you what these data structures are, what the contents are. Okay? All right. So here, one of the pieces of guidance that I'd given before was when you call get successors, that's going to have an impact on the instrumentation that ultimately AutoGrader uses, right? One of the things it records is the states that it visits. So absolutely get successor here. You could start again at the start state, but what's going to happen, it's going to record that you visited that first state when you call the get successor, and it's going to confound the AutoGrader. So if you don't want to call get successors unless you quote unquote really need it, right? Because that's going to end up in the trace that's used to do your scoring. And so in my first implementation of the solution, I had the correct algorithm, but my first state where I started appeared twice on the list, and it was failing my solution. What's going on? I know this is how it works. And it was that call to get successors, which was confounding it. Even though I said do start state and then get successors again, right? So you want to be careful for any time. You want to be careful not to call get successors unless it's actually part of your algorithm. Separate the checking of things from the implementation of your algorithm. Okay? Questions? No? All right. So let's take a look. And I'm going to kind of look back and forth between my printout of my solution and the screen and just kind of walk you through some of the mind space. So we said that depth first search, it uses a frontier queue. Okay. And so that frontier queue, what are we going to use for a queue? What type of queue? I'll ask you. A stack. So LIFO queue, QUEUE for DFS. Okay, so we're going to use a stack. And so we're going to say frontier is stack. And I might need to do some imports along the way. And so I hate this recommendation stuff. Stop. And so now we want a reach data structure, right? That's part of the exposition of the algorithm. Okay, so what are we going to make reached? You can do a bunch of things. What are your ideas? Yes. What's your name? Vincent. Vincent. A set. You could use a set, you could use a hash table, you could use dictionary, you might use dictionary for everything. So it doesn't really matter what you use. Well, it kind of does matter. It does matter if you want to use this reached queue and do updating, then you're going to need a dictionary, right? But a set is perfectly fine. It's questioned. Sure, yes, yes. I'm going over the mind space. I'm not going to implement it for you, but thank you. Yes, you're right. You have to make sure you're using the right versions from the right parts of the code base. Okay. All right. So now, so let's say reached is a set. Okay, that's a perfectly fine. And then in the exposition of depth first search, breadth first search in the book, they're returning the node. But we don't want to return the node, we want to return the actions. And so we're also going to maintain or need to maintain a list of actions in the order in which they were applied to get to nodes as we reach them. And we want to pass that thing along with the nodes themselves. And in that case, the action is the list of actions we're interested in that gets you to that node. Because at the end of the day, when this DFS returns, we need to return the complete action sequence to the goal. So we need to carry that piece of information around with us. And we're going to need to build that incrementally as we go along. So I'm going to call it action list. And it's initially going to be empty. And we're going to make copies of this, add to it, and then associate that with each node as we expand the frontier. We're not going to pass a reference to it because we don't want to maintain references to the same data structure. We want a unique data structure because it's a different list that we carry with each of the nodes that we encounter on the frontier. Does that make sense? All right. So we start out And we'll say, here's our starting state. I hate this. And we're going to go to our search problem, which we're passed in. All right. So we get our start state. And you could say explore the start state, but you want to maintain discipline that everything you expand should be off the frontier. So we're going to seed our frontier as the algorithm goes in the pseudocode by pushing that encoding of the start state onto the frontier. Now, of course, our quote unquote state is going to be a tuple. One of the components is going to be that location. The other is going to be the prevailing list of actions. And then the last thing is going to be the cost. And so we'll push here. We're going to say start state, action list, and the cost is going to be 0 because we're at the starting. Does that make sense? All right. And so this is a direct translation of, well, this is, you can think of it as pseudocode that looks like Python, right? So now, of course, we want to iterate over popping off or taking off nodes off of the frontier, right? So a while not, oh, I hate this, frontier is empty. What are we going to do? All right. Well, we're going to pop off the frontier. Okay. So we're going to say state, action question, action sequence, cost. I hate this. I hate this like code completion thing. It bugs me. All right. So now, okay, we're going to first ask ourselves if this thing that we got off the frontier, is it the goal, right? Before we expand it. So we're going to check for goal of state. And if this is not actual code, pseudocode, I'm just being descriptive here, equals true, right? Then we're going to return the action sequence. Okay? Nope, I'm so used to Java. So once we pop off the frontier, we do our goal check. And then we want to see, have we been here before? So if in reached state, I'm being descriptive again. I'm not literally programming. Yes, Luke.
Sorry, so you're calling action list and action sequence. Are they meant to be the same thing?
Well, I use a different name.
Okay.
So this is assigning to the symbol action sequence what was action list when it put it on the frontier. Absolutely. Any other questions? No? All right. So now, and we'll continue on tomorrow in lab with more code walkthrough. So now, if it's reached, then we want to add this to reached. Add to reached set. Okay. After we've added it to reach set, we want to go ahead and get the successors. Now that we know if we've encountered it, we're going to go ahead and record that, and we're going to explore that, right? So we're going to say, okay, successors list, and we're going to call from the search problem, passed in, get successors. Okay. So now that we get successors, you need to give it the state when you get successors because it's generic function. We're going to go ahead and we're going to iterate on each of the successors that is in that list of successors, keeping in mind that what's stored is that 3 tuple, which has the position in the maze, it has the action list, and then it has the cost, okay? So we're going to go ahead and iterate for successor um, action and step cost in successors list. Now I'm going to go ahead and do something. So for each successor, I know that that successor is going to have a cost of the cost of the node I expanded plus the step cost, right? And then I also know what action from that node brought me to the particular successor. So I can take whatever the action list was and add on to that. And that modified action list is now the incremental set of actions that gets me to that successor. Does that make sense? All right. So I go ahead and I'll say the child action sequence is equal to action sequence. I call it sequence. Let me make sure I'm consistent here. Frontier. Yeah, action sequence. I think I call it action seek. All right, action seek dot copy, right? I'm going to make a new copy of the action sequence of the node I expanded that got me the successor. And then I'm going to append to that child action sequence that action, which is the single step action that got me to that successor. So now at this juncture, the child action sequence is that list of actions that got me ultimately from the starting state up to this particular node that I just encountered. Does that make sense? Any questions? No? All right. Check the time. So once I've done that, I also want to compute the child cost. The child cost is just the prevailing cost, and that's the cost of the node that I expanded that got me the successor, plus the step cost. That's the step cost to get from this node, that node that I expanded to this particular child. Okay. And that child cost is now the cost to get from ultimately that starting node up to this particular node that I just encountered. Okay. So once I do that, I'm going to now add this encountered node to the frontier to make it a candidate for further expansion to grow the frontier. So I'm going to frontier push, and the thing I'm going to push is a triple, and that triple is going to be my successor. It's going to be the child action sequence, and it's going to be the child cost. Oh, I hate this completion. I really loathe this completion just because I might just turn it off. It confounds when you're doing pseudocode things, right? All right. So now the last thing we're going to do is we're going to return the action list. Now, this return of the action list, and you get rid of the raise not defined exception because that'll, just need to take that out. Now, this action list, if we exit this block by this return statement, it's going to be empty, right? Now, up here, when we have the goal condition check, most of the time, well, if you have a solution path, it's going to exit the block here. I always like to use variables for things. Did I need to say return action sequence, action list? No, I could have said return open square brace, close square brace. That's perfectly Turing complete as a program. But again, I like to write for debugability, right? To be able to check things in the IDE environment. Let the tools do the work for you, right? You could use lambdas, you could do implicit array creation, fine, that's great. But it's harder to debug. So let the debugger help you out, okay? All right. Any questions? No. Now, this is not code, this is pseudocode. I'm going to stress that again. I'll leave it to you to actually make it into code. Question, Vincent? No, it'll find the path. Um, this first three, or really four questions, is just your translation of the basic algorithms into code, right? And I highly recommend that you look at things in the debugger. You're welcome to, chase through the definitions and go to game state and go to game state data and all of that good stuff. But the debugger will bring it to you just if you assign it to a variable. Just inspect it, take a look, right? It'll save you a lot more time. The walkthrough will help you figure out how things connect together, okay? So be efficient, work hard, but also work smart, all right? All right. So if you can do, and I'll end with this, we only have 3 more minutes. If you can do depth first search, it's just a one-line change to make it breadth first search. The only difference is you're using a queue for your data structure instead of a stack, right? If you're doing uniform cost search, the only difference is you're using a priority queue, right? And so the beautiful thing is just by changing the criteria for how you select nodes off the frontier, entirely changes the behavior of the search. And as we saw, depth first search is more memory efficient than breadth first search. Okay. All right. Any questions? So hopefully this is helpful. But literally, it's a translation of the pseudocode. And the only difference in the pseudocode, they want you to return it prescribes returning the node. But in this case, you're not returning the node, you're returning the action sequence. So you have to have those action sequences stick around, hence a 3-tuple that you put on the frontier. Okay. All right. Any questions? Is this helpful? All right. Awesome. All right. So please argue, discuss, debate with one another. You're welcome to do so on the Slack channel, and we'll see you all tomorrow.